All right, here we go with the first warm-up problem. So, where on, given this equation, where is my, whoa, tap the brakes, is my center? 1, comma, -2. It's fixed now, okay? All right, so I'm going to go over to 1, comma, -2, and I am going to put a C for my center. Okay? Not setting the world on fire. What do I do next? A and B values? Okay, so A is going to be what? A squared is 25, so A is 5. So what do I do with 5 units? Left to right from my center, right? Okay, so left 5, 1 and 2 and 3 and 4 and 5. Right 5, 1 and 2 and 3 and 4 and 5. Okay, B value. B squared is 4, so B is 2. So that means I go from my center, I go up and down 2. So up 2, 1 and 2, down 2, 1 and 2. Okay? So that gives me the framework for my ellipse. Now I can draw it in. Okay. There it is. Looks fantastic. Probably the best ellipse that I've drawn all day. Okay. Now, foci. We didn't tell you that you had to put the foci on this one, but if I was going to find the foci, the formula that I would use would be c squared is equal to a squared minus b squared, and I take the absolute value of that. So that's going to be, in this case, 25 minus 4, which then that means c squared is going to be 21. So c is the square root of 21. Yes? Okay. Now, square root of 21 is like 4.5-ish. Right? Probably like 4.6-ish. Okay? But on the actual, where the actual two foci are, they are going to be left and right because it's stretched out horizontally. They're going to be left and right from the center. So I am going to add and subtract the square root of 21 from the x part. Okay. Now, if that were an actual number, like if it had been the square root of 16, I would actually add 4 and subtract 4. Okay. But it's not, so I won't. Okay. Oh, that has 2 points anyways. Yep. Yep. They're right here and right here. Okay.
Wait, so if the center was at like 2, -2, then it would be 2 plus or minus the square root of 21?
Comma, -2.
Okay.
Yep.
So is it 0, 0?
Then it would be plus or minus the square root of 21, comma 0. Yep. Unless it was stretched vertically. Then if it's stretched vertically, then I add or subtract it to the y value. Whatever that major axis is, that's what I add and subtract it to. Okay? Right? Good? Let's try another quick one of this one, but let's go in reverse. So here's the picture of the graph. I would like you to find me the equation of the ellipse and the coordinates of the foci.
Is this with the formula of sine squared?
Kind of. Okay. So, where is my center? Where's, do we agree with -3, comma -2?
Yes.
Okay? So that's going to become, it's going to become x minus negative 3, quantity squared, all over something, plus y minus negative 2, quantity squared, all over something, equals 1. Okay? We just got to find that something. Okay? So I'm going to go over here and I'm going to say, well, that distance right there is 5, which means then that this down here is 25, because that's that distance squared. Then I'm going to go back over here and I'm going to count this distance, and that distance is 8, which makes this over here be 64. Okay? So that is the equation, right? Now I've just got to use that equation to figure out where my foci are. C squared is going to equal the absolute value of a squared minus b squared. A squared minus b squared is going to be negative 39. The absolute value of negative 39 is positive 39. So my c value is the square root of 39. Not simplifiable. Okay? Now, which way is my major axis? Vertical or horizontal? It's vertical. So that means I'm going to add my c value to my y part of the center. So that tells me then that the foci are at negative 3, comma, negative 2 plus or minus the square root of 39. Okay? Good? So a hyperbola, which is what we're going to start right now, okay? A hyperbola, in an ellipse, the distance to those foci we added, and it was a constant. In a hyperbola, that distance to the foci, we're going to subtract, and it's going to be a constant. So it's very hard for me to show you the distance of on a nice big old board like that for a hyperbola, because you're subtracting. Now, I could show you a bunch of mathematical gobbledygook by clicking on this mathwords.com/h/hyperbola, but I'm not going to. It's not what I really wanted. I wanted it to be like if you watch the video of the ellipse, we had an animation where it showed you that distance was always a constant, and it's hard to do with subtraction. So let's just dive headfirst into the pool. Or, sometimes when you get taught how to learn how to swim, you just dive into the pool. Okay? So, here, let me extend that page up a little bit. Here are the two formulas, the two general equations, the two general forms, however you want to call it, of a hyperbola. Okay? One thing that you should notice in that it's different from a circle and it's different from an ellipse in that we are now subtracting the squared terms. Okay? This hyperbola is the only one that you subtract the squared term. In a circle, you add the squared terms. In an ellipse, you add the squared terms. Okay? So depending upon which is which, okay? So if it's x squared minus y squared, that's a left right opening hyperbola. If it's y squared minus x squared, that's an up-down opening hyperbola. Okay? So we're going to need to know which one's first. Okay? So far you should have noticed the pattern between all of them because we've kept the pattern the same throughout all of them. Okay? X goes with H, goes with A. Okay? XR if you want. Okay? What? Hax. Hax is a good one. Okay? H-A-X. Okay? And now that opens, and that is left and right in hyperbolas. Okay? In an ellipse, hax is it's elongated horizontal. Okay? In a circle, it's just hax. It's not even hax. It's just HX. Okay? Okay? YKB, bike, bike. What? What do you got? Bike. I go bike. Okay? UYK. Yeah, exactly. Totally different octave of voice, but we'll say it was Frank still. And then that's up down. Right? Now, there's going to be there's hyperbolas we saved for last for a reason. Okay? There's a lot of work involved with the hyperbola. Okay? It's doable work, but there's a lot more work involved with it. So let's dive in and let's go. Let's do this. So excited. Okay? So, here's some different real-world hyperbolas. Okay? Radio signals, the hourglass, the McDonald Planetarium in St. Louis. My two favoriteest one are sonic booms. One, because sonic booms are pretty cool. Okay? Unless you're a window, then a sonic boom's not really cool. Okay? But if you're just standing outside and you hear a sonic boom, it's actually pretty cool. Okay? But the cool one is if you had a lamp. I love lamp. Okay? Anchorman. Okay? I love lamp. Okay? So if you clear everything away from the lamp and you have the lamp up high enough, okay, you'll see that there is a parabola type looking thing up top above the lampshade, and then there's one below the lampshade too. Okay? And that makes hyperbola. Okay? Especially if your lampshade is a cylinder, one of those, because then it makes it, it's not bigger. The one like this lampshade would produce a bigger one on the bottom because the lampshade's bigger on the bottom. In a hyperbola, they're equal. Okay? Yeah, buddy. So, navigating our way around hyperbolas, we're going to end up graphing x minus 3 quantity squared divided by 9 minus y plus 2 quantity squared divided by 16 equals 1. We're going to graph that in the next 20 minutes. Okay? Not even going to take us that long. Maybe it'll only take us 15. Okay? All right? So the first thing that we want to do, the first thing that we need to do, is we need to figure out which way that this hyperbola is going to open. Our choices are left, right, up, down. And remember, it all depends upon what? What does it all depend on? What do you guys press? Starts first, okay? So when x started first, which way did we say that one was? Left, right. So this is a left, right opening hyperbola. Okay. We'll need that a little bit later on in the problem to graph because we need to know where our vertices are. We need to know where the parabola is. Okay? So we're going to need that in a little bit. Left, right, opening parabola. Love it. Next, we're going to find the center. And we're going to do that just like we did before. Okay? So that's going to be h comma k. H goes with x because it's part of hex. K goes with y because it's part of the bike. Okay? All right? So where is the center of this hyperbola? What did you say, Frank?
3, -2.
3 comma -2, did you say?
Yep.
I love it. I couldn't have said it better myself. Huh? So our center is at the point 3 comma -2. All right? Well, let's put that on there then. So if my center is at 3 comma -2, that's going to be right there. All right? So we put the center right on the graph. Okay? It's technically not part of the hyperbola, but it's the middle point. It's kind of the, everything revolves around it. It's the nexus of this hyperbola's universe. Okay? Second step, we are now going to build a box. It's not going to be like Build-A-Bear. Okay? Build-A-Bear ran a promotion last year, or in the past, where it was like, come in and you can build a bear for your age. You know, for the price or the cost of the bear is the cost of your age, or however old you are. And people waited in like lines, and then people got angry because they were waiting in lines, and it just was mass hysteria. Our building the box, we could have had it done already. Okay, so take the square. So we're going to look under x squared. So under the x squared term, well, that's a, right? So I'm looking at my a value. My a squared term is 9. So what's my a then? 3. So I'm going to go from my center. I'm going to go left 3, and I'm going to go right 3. 1, 2, and 3. 1, 2, and 3. Okay. Now I'm going to put a line. I'm not going to put a dot. I'm going to put a line here because I'm building a box. Okay. Good so far. All right. Boom. Let's do that again. So I'm going to reset this one. So there is my center. Here is my left side of the box. Here is my right side of the box. Now I got to figure out how tall my box is going to be. So I'm going to look underneath the y squared term. Well, that's 16. Again, that's b squared. I need b. So I'm going to take the square root of that. That gives me 4. So from my center, I'm going to go up 4, and I'm going to go down 4. 1, 2, 3, and 4. 1, 2, 3, and 4. Okay? So now I have those 4 dimensions. So for you, I would lightly draw the box. I don't have that option because I'm not that, technically sound, but I am going to lightly draw in my box. So there's my box. That's kind of like a no-fly zone. Okay? Nothing's going to be in that box, okay, other than the center. And we might cut through it with a line or two, but nothing else. The hyperbola will not be inside of that box. Okay? So, let's go on to the next step. Step number 4 says I need to form the diagonals of the box because that's going to give me my hyperbola's asymptotes. Okay? So I'm going to draw in the diagonals of said box. And when you draw them in, you will want to draw them in as far across the graph as you can. because that's going to be where the hyperbola goes. That's going to be my boundaries of my hyperbola. So I want to draw them in as best I can. So I want to go as far across the graph as I can. Okay? Now, because we have those wonderful lines that are asymptotes, we should be able to come up with those asymptotes equations. Okay? Now, here's the cool thing about hyperbolas. The slope of the asymptotes is equal to plus or minus b over a. Always. Because if you think about it, those lines go through the center of my box and they go through the corners of my box. Right? Well, if I go over here and I count my rise, 1, 2, 3, 4, and then I run 1, 2, 3, that's 4 over 3. It's always going to be B, my rise, over my run, A. Okay? And to go to one, it's positive. To go to the other, it's negative. So my slope is always going to be plus or minus B over A. I just need to spread that out onto each one. I can't just use it as plus or minus. Okay? So let's call this one asymptote number 1, and we'll call this one asymptote number 2. So if I want to find the equation of asymptote number 1, that's going up and to the right, so that tells me that it has a positive 4/3 slope. It also happened to be that the corner of the box was on the y-axis. So if I count 1, 2, 3, 4, 5, 6, and that gives me a y-intercept of -6. So right from there, I can come up with the equation of that asymptote. So my first asymptote has the equation y equals 4/3 x minus 6. If it's not, if the side of the box is not on the y-axis, then you have to use point slope form. Given the slope and the center, use point slope form to find the equation of the line. Okay? Asymptote number 2 has a slope. This is my negative slope now. Okay, that's a bad 4, but we'll let it slide. Okay? And it has a y-intercept of positive 2, because that's where that corner is, right there. So the equation of this line is y equals -4/3 x plus 2. And those are the two equations of my two asymptotes. Okay. Next, we can find the two vertices. The two vertices are going to be the midpoints of the sides of the box that you just made, okay? In the direction that you're opening. So our open was left and right. We decided that before we even started. So I want my vertices to be the midpoints of the left and the right side of the box. So that's going to be straight out from the center. So there's one vertice. There's the other vertice. Okay? So this is 1, 2, 3, 4, 5, 6, comma, -2, and 0, comma, -2 are the equation, or excuse me, are the coordinates of my two vertices. finally, what we can do now is we can now draw in our hyperbola. Okay? So let me go back up here to this one. Let's pick a nice, brighter style color. Let's go with that one. Love it. Excited to be part of it. And there is our hyperbola. Okay. Oops. Did it again. Step 6 was drawing the, step 6 was drawing the hyperbola. So step 7, our last step, clearly we got the most steps involved because it's the most involved one, is we need to find the foci. The important formula for this foci, or for these foci, is a squared plus b squared equals c squared. Okay? I've seen that before. Okay? Pythagorean theorem. Okay? A squared plus b squared equals c squared. A squared is, again, the number underneath the x term. B squared is the number underneath the y term. C, then, that C value is going to be the distance from the center to the focus in both directions. Okay? In this case, because it's a left-right opening per hyperbola, it's going to be to the left and to the right. If it were an up-down hyperbola, it would be up and down. Okay? So a squared is 9, b squared is 16, so that means 9 plus 16 is 25. Okay? So c squared is 25. So c then is 5. Okay? So I put the plus and minus in there because we're going to have to go positive direction and we're going to have to go to the negative direction. So since it's opening left and right, that gets added to the x part of the center. So that tells me then that the foci are located at 3 plus or minus 5, comma, negative 2. Now the question came up last hour in the Resource Center. Can I leave it as 3 plus or minus 5, comma, negative 2? And my answer is no. If it were 3 plus or minus the square root of 5, comma, negative 2, yes, you could leave it like that. But here, we can do that math. We know what 3 plus 5 is. It's 8. So write 8, comma, negative 2. We know what 3 minus 5 is. It's negative 2. So write negative 2, comma, negative 2. Okay? So when you can do the math, do the math. When you got to radicalize something, leave it in radical form. Okay? So that puts my two foci, 5 out, 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5.